Would you like to start or should we wait?
I think we can start now, and then I can admit people who are gonna come.
Yes.
Yes, welcome everyone. Today it's my privilege, it's our privilege to have Dr. Zoe Cournia with us. She has an extensive experience in molecular dynamic simulations. Also, she's the editor of GCIM. So today she's gonna share her insights about protein and different binding partners, interactions with different binding partners. So the stage is yours, Dr. Cournia.
Thank you very much. As mentioned, I'm Zoe Cournia. I am a chemist. I studied chemistry at the University of Athens. And then I went for my PhD to the University of Heidelberg when I studied biomolecular simulations with Jeremy Smith. And then I moved across the Atlantic to go to Yale University in the Department of Chemistry to study computer-aided drug design with Bill Jorgensen. And I will show you today how all these fields can be combined. And also in the questions, feel free to ask me how I decided to go to the US or how I decided to do a PhD. Also, all the questions are good questions. So the title of my talk, as mentioned, will also present biomolecular simulations, also taken from the angle of computer-aided drug design, in predicting protein-ligand, protein-protein, and protein membrane interactions using molecular simulations and artificial intelligence. I am now a director of research at the Biomedical Research Foundation of the Academy of Athens in Greece. So our lab focuses on protein membrane interfaces in drug design. So we study hit identification and lead optimization, peripheral membrane proteins, how they interact with the membrane, and whether these could also be potential drug targets, but also transmembrane proteins. And here you can see a summary of our publications for these topics. So in protein ligand structure and free energy of binding, so predicting the protein ligand binding essentially boils down to two key questions. First, what is the structure of the protein and the ligand? So this is the docking problem. Then we have the scoring problem. What is the free energy of binding of the ligand on the protein? And also, if you have two ligands, what is the difference of the free energy of binding between the two ligands on the protein? In other words, which of the compound will be preferred for binding on the protein A or protein B? So recent advances in free energy calculations, algorithm, and computational power have allowed the rigorous calculation of the differences in free energy of ligands, congeneric series, using alchemical free energy methods, and also ultimately of the absolute free energy of binding. Why am I talking about lead optimization first? Because lead optimization is the most preclinical phase. If you look at the diagram timeline of the preclinical drug design and drug development, you see that lead optimization is the most expensive phase. And that's, of course, not only due to the protein ligand binding affinity optimization problem, but also due to extensive metabolism, pharmacokinetics, pharmacodynamics, formulation, and other causes. However, here we will study how we could improve this very expensive phase, the lead optimization phase, using computers in terms of affinity. In other words, if I have a molecule that has a potency, let's say this is an IC50 concentration, this IC50 means what is the percentage or the concentration of the molecule that is required to bring down the activity of the target by 50%. So here, this molecule that is an inhibitor of the actin-related protein 2 and 3, so the polymerization of actin, has an IC50 of 12 micromolar, and that means that 12 micromolar are needed to bring down the activity of the actin-related protein 2 and 3 by 50%. So 12 micromolar is actually a high concentration, and this high concentration can also produce side effects, meaning that this concentration of the molecule is high enough to go and stick to other proteins as well, producing undesired effects. Therefore, in lead optimization, what we are aiming to do is to add and remove substituents in order to improve the potency, and that will lead, hopefully, to improved prediction methods to lower the cost and increase success rates using computational techniques. So here, having this scaffold, we want to optimize it, hopefully to nanomolar affinity, by adding and removing the substituents. So, for example, you could add chlorines, you could add methyl groups, you can have two groups here, chlorine and fluorine, or you could change the rings, change the linkers. But the question remains, what is the difference of the potency between this parent compound and all the analogs? In other words, we want to compute the difference of the free energy of binding between this parent ligand and all the rest on the target of interest. And this, if we have a method to do that, obviously we will spend less time and resources in the organic synthesis lab because we will be able to predict computationally the differences in the free energy binding affinity, and we won't have to synthesize and do all the assays, which is costly and actually time consuming. So a rigorous computational framework to compute these relative binding free energies within a set of similar ligands, which we call congeneric ligands, is the free energy perturbation theory that states that relates the free energy difference between compound A and compound B, so this could be compound A and compound B, to an average of a function of their potential energy difference by sampling for the reference state. So to explain this a little bit more clearly, what we are aiming to do here is actually to calculate how ligand A binds onto the protein. So what is the free energy of binding on this protein? And how does ligand B bind on to the protein? What is the free energy for ligand B to bind to the protein? However, these processes are slow to compute. So we have to find an alternative. So this method that I just explained, what we can do with this method is to close this thermodynamic cycle and to transform a ligand A to ligand B in solution and inside the protein by calculating delta GA and delta GP. Because this is a closed thermodynamic cycle, the summation of all the delta G's around the cycle should be 0. So delta G1 plus delta GA minus delta G2 minus delta GB will actually produce 0. So here you see delta G2 minus delta G1 is equal to delta GB minus delta GA. So essentially, if this delta G2 minus the delta G1 is less than 0, is negative, that means that ligand B binds with higher affinity to the protein. Equally, because we have made this equation, if delta GB minus delta GA is less than 0, that means that ligand B is favored for binding. In order to create sampling for this calculation, we can use Monte Carlo or molecular dynamics. So we use this trick to avoid calculating the slow processes. And actually, these calculations, they start by mixing essentially the parameters of the two end states. So if we have ligand A and ligand B, let's say that they differ by a chlorine atom. So this one has a fluorine atom and this one has a chlorine atom, so fluorine and chlorine. What we are going to do in this leg and in this leg is that we are going to transform the parameters of the first ligand, which is fluorine, 100% fluorine, to chlorine by essentially mixing the parameters of the two states by very slowly perturbing this potential energy function by linear transformation of the potential energy. And we can do this in different steps, which are called lambda windows. So this is essentially a linear transformation of the Hamiltonian that transforms the fluorine to the chlorine in very small steps. Obviously, this is not a realistic process in nature. That's why we call it alchemical free energy calculations. This can only be done in the computer. However, because this is done in very small steps and it is a computational empirical method, it is possible to do it. And we have seen that if you have the right conditions, which we will explain in the next slides, you are able to generate very accurate free energy differences and free energies of binding. This technique is not new. Actually, the first application of free energy calculations to the salvation of organic molecules was published first by Bill Jorgensen and his colleague at Yale in 1985. And the first applications of free energy perturbation in ligand protein systems in 1989 and 1984. And also for protein stability. And here you can read some nice reviews. So we applied this technique in a set of congeneric series. As mentioned, congeneric means analogs. These are spirocyclic compounds that bind on a receptor that is called the farnesoid X receptor. This was part of a blind affinity challenge where we actually didn't have the experimental data at hand. We only had these molecules initially. And the organizers of this drug design resource challenge, drug design data resource challenge, or D3R, they asked us to produce the difference of how these compounds would bind on FXR based on a parent compound. And that was the task. So initially, the organizers of this D3R blind affinity challenge, they didn't provide anything as mentioned, only the structures of these molecules, not even the structure of the protein. So we had to look online to find in the protein data bank the structure of the FXR, to choose an appropriate structure and perform these calculations. So here I'm plotting the predicted values versus the experimental when they were released after the challenge was over. And we could see that we got a modest correlation between the predicted and calculated structures. However, at the next stage, the organizers of this challenge also gave us the ligand protein crystal structure where we could actually start from. And you can see that there is a dramatic improvement of the correlation when you actually know the protein ligand structure. So here we used Schrödinger FEP+, and as you see, the slope improves with known crystal structure. And if you're more interested in these results, you can read our publication here. Also, the virtual screening showed that there is no correlation if you dock all these compounds, dock and score with virtual screening programs. There was no correlation with experimental results because docking and scoring are not sensitive to the very, very, very small changes that these molecules have. So you see here that they basically differ. So this is a thiophane, and the change here is like you have a methyl group here, and the thiophane is changing to a chlorobenzene, and that's the only change. So it's like very, very small changes that docking cannot pick up, docking and scoring. However, we also know that the method has a limitation, and that is that it cannot predict ligands that are within 1 to 2 kilocalories per mole. In other words, the error of the method is below 2 kilocalories per mole. So if you produce a very narrow experimental range, this is delta G experimental between 1 kilocalories and 3 kilocalories. This is within the error of the method. So even if you don't know the crystal structure, or you know the crystal structure, the protein-ligand complex, it won't make a difference. The method cannot be predictive because the experimental binding free energies are within 2 kilocalories per mole. So therefore, one has to take care to have diverse ligands of diverse binding affinities. So these calculations, relative binding range calculations, can also aid in identifying ligand binding modes. So we devised a strategy for that. First, we dock in the native ligand X-ray structure. We align to unknown ligands, not with docking, but with maximum common substructure. Then minimize, and then we can start the calculations. And here the question was whether we can predict the crystal structure of the unknown ligand, which is here's the chlorine. And the question was whether the chlorine group would be facing this direction, ortho. This is ortho, but this is also ortho. However, in the crystal structure, what is the most preferred, this or this? The calculations showed that if we have the two ortho possibilities, because, okay, in reality, ortho, of course, it's equivalent in solution, but in the protein, it's not equivalent because there are different interactions here and different interactions here. So one of the two ortho positions is preferred. So we did a calculation between this ortho position, and to close the cycle without any chlorine in the ligand. And we concluded through this closed thermodynamic cycle that actually the chlorine position would be favored here. And indeed, when the crystal structure came out in this D3R challenge, we could predict it with an RMSD of 0.3, and you see that in green is our predicted pose, and the orange is the crystal structure. So we have a very good agreement. It should be also noted that these calculations, they work with usually with our native environment. So if we tried a transmembrane protein where we fixed the backbone and we created a water box around it without the lipid bilayer, and the calculation failed to correlate experimental differences in free energy of binding with calculated differences in free energy of binding. And you see here there is no correlation between these two. But when we embed now the protein in a lipid bilayer and we leave it fully flexible to adjust its dynamics to the environment, then we can resurrect the correlation between the calculated delta delta G and the experimental delta delta G. If you're interested, here are the publications summarizing these results. So before performing these accurate relative binding fringe calculations, one should take care of the following issues and factors. First of all, as we already saw in the slides, the input crystal structure has to be of a high quality. If you don't have the crystal structure, or if you are trying AlphaFold, you are not going to have as good results, because the input of the coordinates really matters for this calculation. Also, the protein structure may need to be flexible in its environment, as we saw in the case of the M2TM channel and the lipid bilayer. Also, sufficiently long simulations are needed and methodology to overcome barriers, so good sampling. Of course, the method is sensitive to the force field, or we can term it as scoring, but it's really like a potential free energy function, potential energy function. We have to ensure that the perturbations are not too big, so normally up to 10 heavy atoms, because if you want to sample the two ligands that are analogs, if you make very huge changes in the substituents, then you are not going to achieve efficient sampling in order to overlap the two end states. So we have to do only very minor perturbations or changes. The error of the method, as mentioned, is within 2 kilocalories per mole, so it doesn't make sense to try to predict the difference in the free energy between a compound that is 10 micromolar and 12 micromolar. the method cannot tell you that. If you have large-scale protein movements, then you are not advised to use these methods because these large-scale protein movements cannot be sampled sufficiently within the time frame of these calculations. And also a specific protocol has to be followed: ligand alignment to a reference ligand structure, investigation of buried waters, carefully selecting the mutations, and investigation of whether you are changing your occupancy, meaning whether you are sampling to ortho or meta states. Yes, we discussed that. This is a review that we wrote, just in case you want to read it. And also because these tools are very difficult to prepare, we set up also a tool which is online, and it works for relative binding friendly calculations in NumD. So this is called FEPrepare, and basically you upload the reference ligand and the mutant ligand, and then you upload your files, and then you download the final setup for running this calculation. So now moving on, we discussed the protein ligand difference in free energies of binding. Now we can discuss how we could compute not only protein ligand free energy of binding, but protein-protein free energy of binding. Again, we have the same issue as discussed before. We have the sampling or docking problem. So first consideration is how does the protein-protein complex look like? What is the structure? Then you have the scoring problem, meaning what is the free energy of the binding of the two protein of dimerization? And when these proteins bind on the membrane, what is the structure and what is the free energy? To study this problem, we were driven out of curiosity for a project that we are currently running on KRAS. KRAS is a small GTPase associated with 30% of tumors. And essentially, what we know is that KRAS recruits this RAF kinase to the membrane, where it acts as a scaffold for RAF activation and signaling. So when KRAS dimerizes on the membrane, it recruits this RAF dimer and it scaffolds it. And when the binding of RAF and KRAS happens, then essentially the signal is to the cell to proliferate. And the KRAS mutations facilitate the dimerization on the membrane, causing aberrant signaling. However, we did not know what is the structure of the KRAS dimer. Of course, as many people, the first thing that we wanted to do to get the structure of the KRAS dimer on the membrane was to go to AlphaFold multimer and AlphaFold 3. However, we found that while AlphaFold 3 and AlphaFold multimer could produce the structure of the KRAS monomer with very, very high fidelity, it could not produce it for the structure of the dimer, showing a very low PLDT score. Therefore, we wanted to proceed with calculations of molecular dynamic simulations to see whether we could find any other conformations. Because we had one crystal structure of the dimer, but it was in water, not on the membrane. So we investigated, we placed this structure on the membrane and on two membranes with a different concentration of a signaling lipid PIP2, simulating with and without effectors, and also performing Markov state modeling to find the dominant conformations. So here what we found is that when we place the crystal structure on the membrane in a low PIP2 concentration, then the dimer was dissociating. But when we increase the PIP2 concentration, then this complex is retained, and also that effectors stabilize the complex irrespective of whether we increase or lower the PIP2 concentration. However, we knew that these calculations are for one structure, which is called P5VQ2. And in the meantime, another structure appeared, the 6W4E. And we wanted also to check this one. They are quite similar, so just the orientation of these alpha 5 helices is changing. We turned then to still unbiased simulations, but called adaptive sampling, where essentially you are running very short molecular dynamic simulations, and from each simulation you are taking the lowest probability state, so the state that has the lowest probability, and from that you spawn or you start new simulations, hoping to escape the free energy minimum that you are currently located and to overcome the barriers. We saw some more movements, but however, we found that the maximum that we could get, this is the starting situation, so we could get one more minimum and one more minimum here. And after running very long simulations that took a long computational time, we found that we could not really go very far. This is the measure to measure how far you are from the initial structure, just 5.9 angstrom, which is quite low. So we concluded that this was not a method that we could use. And then we turned into coarse-grained simulations, which is a method where you can achieve a more efficient sampling, because our goal was to overcome the fringe barriers and to go to another minimum, trying to simulate what would be the best or the most preferable conformation of the KRAS dimer on the membrane. And because we couldn't do it with atomistic simulations, which of course have very high resolutions, but are insufficient to study the phenomena of interest within the time scale that they can achieve within their very computational extensive resources, we turned into coarse-grained molecular dynamic simulations using a force field that's called Martini 3, where atoms are grouped in larger beads and the system reduces its complexity, enabling for studying longer time and length scales. And it is actually validated a lot. So here you can see that when we have a lipid molecule, normally it has 130 atoms. You can see it here in the back, but you can group the atoms in beads, and then you can turn this fully atomistic model in a bead model where you are achieving a very, very big speed up. Moreover, not only to speed up the calculations, we didn't only use the coarse graining scheme, but also metadynamics, which is a method to bias the simulation towards a desired direction. So here, as I mentioned, we want to study what is the dimerization of KRAS on the membrane. So what we are doing is we're filling the potential free energy landscape with energy in the form of Gaussians. We define a collective variable, which in our case is the two proteins coming together, and the actual structure of the dimer in terms of root mean square deviation. And by filling the potential free energy landscape with Gaussians, you can finally overcome all the barriers and sample the full free energy landscape. And because you know how much energy you provided the system, after you sample everything, you can remove the biases and actually take the correct free energy landscape. And this is what we did. Before we turned into the KRAS system, we wanted to validate the methodology. And to validate the methodology, we actually turned into 5 known protein dimers. These have known structures, experimentally resolved, and most of them have also known experimental free energies of dimerization. The insulin dimer, the Barnase bar star dimer, and the RAS-RAF dimer are all solvent water-soluble proteins. And we also took 2 membrane proteins. The FA1 is dimerizing in the membrane, and the rhodopsin is dimerizing the membrane. And here you can see an example of 2 rhodopsin proteins in the lipid bilayer that are dimerizing. So basically you see a lot of transitions between the protein that is in the membrane and the protein that is in the dimer. And when you are sampling what are the free energy minima for these states, you can create maps. I will explain the previous plot, but just to let you know that you can create maps that are free energy landscapes between the collective variables or reaction coordinates that you chose. Here we chose the distance of the two proteins coming together and the root mean square deviation from an initial structure. And so you can actually calculate also the free energy of protein-protein association. How you can do this? By generating potential of mean force curves based on the distance, and by integrating this plot, you can calculate the free energy of association. So I guess here I'm writing the conditions so that we had to shift the distance to take into account the average radial volume of the proteins, to shift the entire BMF to 0 to get the delta G, and to estimate the binding free energies by integrating the PMF, this curve, using this formula. And this is a transmembrane protein, so it's in two directions. So you can get the free energy minima here, but you can also get, you can compute the free energy of dimerization, and you can compute, compare it to experimental results. So here, for example, this FA1, we have an experimental dimerization, 3.68. And you see here that the previous calculations with another force field, previous force field Martini 2, overestimated this free energy of association, but with Martini 3, it's much better. And also the same for insulin. The experimental is minus 7.2, and the integration of PMF finds also a comparable value. So we concluded that in the enhanced sampling simulations, we could always find the free energy minimum that corresponded to the crystal structure that I showed here. We could always recover the structures in the maps. However, they were not always the lowest free energy states. And that means that you cannot say, oh, okay, that this is my deepest minimum, so therefore this is the most preferred structure. No, not with Martini. However, what you can do is with this Martini 3 force field, you can create several solutions on the potential energy fab, several structures, so XP, Z, W, V, and all of these are minima that are potential structures. Then you can actually turn it back to atomistic simulations in a process called backmapping, and you can calculate then with a more accurate force field what is the energetics of the systems. So being encouraged by the system, we decided to move on with studying KRAS. And here to study coarse-grained simulations of KRAS, we had to parameterize one of the structural features of KRAS, which is a farnesylation. It's a post-translational modification that is called farnesylation. And Panos Koukos from my lab and our collaborator Paolo De Souza worked on that. And they created simulations with atomistic force field CHARM36. Then they created the Martini 3 parameters through these simulations, and they could generate coarse-grained simulations with Martini 3, which they then validated, and the results are in this paper. With those parameters at hand, we could now proceed to do these metadynamics coarse-grained simulations. And we found of KRAS, dimerization on the membrane, what we found was that not only we could recover the crystal structure, but we could also recover experimental our model structures that appeared in the literature. And here I'm just showing a plot of many different minima that we found on the free energy landscape between KRAS with RAF and without RAF. So to move on, because I only have 10 minutes left, I will speak about how we could then use this knowledge to target protein membrane interfaces for drug design. Because as I explained, these calculations were very time consuming, so it took us a lot of computational time to calculate the structure of KRAS dimer on the membrane. And we thought, what if we had projects that had 30 proteins? We didn't know the structure of 30 proteins on the membrane, and we wanted to get the structures. Would we have to do coarse grain metadynamics for all of them? We were interested in that problem because the abnormal protein membrane attachment is involved in deregulated cellular pathways and in disease. And we thought that targeting this protein membrane interface is an interesting novel drug design strategy, but has been neglected so far because of the complexity of the interface. The protein membrane interface is not known. Computational workflows to study protein membrane interfaces are challenging, so we wanted to create a computational workflow that would automate targeting these protein membrane interfaces given the scarcity of structural information. So we used the machine learning to do that. So basically, in our workflow here, we start with an ensemble of molecular dynamic simulations, but a small ensemble. It doesn't have to be the extensive one that I showed before. Then we do a membrane binding domain identification using machine learning. We proceed with binding site identification and whether the site is allosteric, and then we do docking and scoring, compound selection, and in vitro assays. Essentially, we want to predict what is the protein membrane interface, what is a site that is druggable on the membrane protein interface, and whether this site is communicating allosterically to the active site. So let's proceed with a membrane binding domain identification using machine learning. Here we have a binary classification problem. The residues of the protein that are depicted here will either bind on the membrane or will be solvent exposed. So that means we have a binary problem. Either the amino acid is contacting the membrane or it is not contacting the membrane. That is called classification. And in supervised learning, which can be subdivided in classification and regression, classification is one branch. So we use classification here, where the task is to train the machine learning algorithm to optimally distinguish the two classes. Will a residue contact the membrane or it will not contact the membrane? So the hypothesis is that we can predict membrane penetrating amino acids. For that, we need input data. What is the data set? It's the peripheral membrane proteins with experimentally known membrane penetrating amino acids. We have to extract features, physicochemical and biochemical amino acid features of the amino acids that contact the cell membrane. We then provide with supervised learning, as I mentioned, because it is a classification problem. And finally, we evaluate the results. Let's proceed step by step. After describing a hypothesis, I will explain the dataset that we considered. The dataset was the 54 peripheral membrane proteins with experimentally known amino acids that we took from the protein data bank. We prepared the dataset by deleting unwanted chains, waters, heterogens, add missing atoms, etc. Then we proceeded with feature extraction. For the data selection, as mentioned, we took these 54 peripheral membrane proteins, which we had to split in a validation and in a training set. We removed amino acids that were inside the protein. Obviously, the amino acids that are inside in the interior of the protein will not contact the membrane. And we also removed non-hydrophobic amino acids. Then we also generated a test set of 11 peripheral membrane proteins that were not identical to the ones in the training set, so that the validation and test sets are unbiased. The next step is to calculate the features. The features are calculated by algorithms. Here we used ensemble tree-based algorithm, and we found that the important features for protein membrane interactions is hydrophobicity, solvent accessibility, and secondary structures. However, we also found also other features that we didn't expect, such as the evolutionary conservation score, the flexibility, and the dihedral angles of the amino acids. Then let's proceed to the algorithm that we used for supervised learning. As mentioned, this is a classification problem. And for the classification problem, we can try many different algorithms because every classifier works in a different manner, has the potential to predict correctly samples that others cannot, and you cannot know a priori which one algorithm is the best for your problem. So with my colleague Alexis Hadjigoulas, who was doing a PhD back then, he trained and validated 21 machine learning classifiers, and after doing hyperparameter optimization, he provided the results to meta-classifiers, which, what is a meta-classifier? It basically takes the results of the 21 algorithms and the different hyperparameters and votes as to what is the best classification scheme for the problem that we want. How does it vote? It votes by taking metrics that are called recall, precision, and F1 score that is based on true positives, false negatives, false positives. And F1 is a mix of recall and precision. So the voting classifier is a majority voting from the first level classifiers. And also a stacking classifier trains the classifiers based on the output of the first level classifiers and takes all possible combinations of the first level classifiers and validates it we validate it for a set of 8 proteins. And finally, the result that we received is that the F1 score is 0.86 or 86% and 0.71 for MCC. The test set predictions showed 91% precision, meaning that essentially you are identifying the correct protein membrane interface regions. They are with red. Here, we also examined the false, apparent false positive cases. You see here, they're not on the membrane, but we found that these residues are actually at protein interface. So another protein comes here and contacts these residues. So the algorithm can classify not only the protein membrane, but also the protein-protein. We compared with other tools that are available for protein membrane interfaces, and we found that our model could predict equal or better performance in the validation set. Although it was not trained on transmembrane proteins, it also produced very good results for transmembrane proteins by having a 93% precision for amino acids that are embedded in the cell membrane. We used these results to then proceed to the ultimate goal, which was drug discovery. For that, we need binding site identification at the protein membrane interface. To target the protein membrane interface, we created a workflow that is called DREAM. It is a web server that you can find here. It predicts protein membrane interfaces. It predicts protein binding sites and protein conformational ensembles, and it is implemented in a web server that incorporates the workflow of conformational ensemble, pocket detection, that ultimately gives you sites that can be utilized for drug design. So membrane binding identification algorithm for generating the protein membrane interface is our ensemble machine learning model, and this is the publication. To generate the conformational ensemble, we used XProZ, and to generate the binding sites, we use another algorithm called P2Rank. This web server was used in prospective applications where people in different groups, this is a group from MIT, they had proteins of unknown protein membrane binding interfaces, and because the protein was huge, they couldn't really do site mutagenesis for like level residue-based mutagenesis to mutate all the possible residues of the protein to find which ones bind on the membrane. For that, they used DREAM, And indeed, they found that the dream predictions were correlating correctly with amino acids that contact the membrane. Basically, they found the dream prediction regions, and they mutated these residues, and then the protein was not binding on the membrane anymore. So it was a validation of our algorithm. And in another case, again, here there were produced proteins, expressed variants after doing a dream calculation and prediction, and the variants or the mutants that were produced were no longer associated with the membrane, validating our algorithm. And yes, I don't know, do I have 2 more minutes to?
Yes, of course,
Or
of course. You can have.
Okay, yes, I'll take just 2 more minutes to tell
Definitely.
you an interesting perspective that we then considered. Um, we found that a dream in a very big protein, it could take hours, so we wanted to make it even more efficient to take minutes or seconds. And we were inspired by the fact that Facebook, or Meta now, produced an algorithm that does not use the MSA that AlphaFold uses. They have a model that is called ESM2 and ESM-Fold, which can predict with accuracy similar to AlphaFold the fold of a protein by not using the MSA that AlphaFold is using, but by using natural language processing. What does this mean? It means that as ChatGPT, what is natural language processing? You all know ChatGPT. It is an algorithm that can recognize our language. It can recognize English, Greek, Turkish, and so on. It can produce new texts. So it seems that it's not only us who have a language that we can communicate with, also proteins have their own language. And this is called the protein language model. So protein sequences consist of 20 amino acid letters. This is similar to an alphabet. And protein sequences can be used as sentences, and their amino acids are the words. So it looks like with taking a sequence of the protein, you can, of many, of course, thousands of proteins, you can produce something that is called a protein language model. And by using this protein language model, you can produce the fold of the protein. So we asked the question whether we could use the natural language processing, so this protein language model, to predict the protein membrane interface without using structural information. So Dimitra Parano in our lab, she took this protein language model, she created a data set, constructed embeddings or features for this language model. She trained machine learning classifiers, and now we will see the results of the embeddings. The data set, in the meantime, because these are now we move on from the classification problem to the deep learning problem. It's still a classification, but it's the traditional machine learning versus deep learning. Deep learning needs thousands, if not millions of data points. And we couldn't do it with the original DREAM dataset, which in the meantime increased a little bit from 54 to 65 proteins, but still was very small. But at the same time, the group of Natalie Reuter published a dataset called Peppermint of a total of 2,500 structures, where they would show the protein membrane interface. And with that expanded datasets, we could now use deep learning. So eventually we selected the proteins and we created 2 datasets. One is just the unit prot sequences, and one was the sequences that were resolved in the protein data bank. And we found that actually when you use just the sequences without any structural data, the algorithm doesn't work, possibly because it has a lot of false positives. So obviously when you when you label all the amino acids based on this database, you are missing some unresolved some unresolved amino acids that may contact the membrane, and this increases the amount of it increases the amount of the algorithm is confused, because if a residue contacts the cell membrane and you label it as non-contacting, then this is a false information to the algorithm. So basically this failed. However, when providing only sequences that were crystallized, then we increased the prediction by a lot. And we showed that the algorithm could indeed provide the protein membrane interface in seconds instead of hours. And however, it could only do it only within the proteins that were in the training set, providing the first proof of concept showing that protein language models can be used for the prediction of membrane interacting amino acids. However, more results are needed to generalize this algorithm to all the proteins existing. Oh, in here you can see the results. Here, for example, you have a minutes case, and here you have just seconds. So I close this presentation by thanking my collaborators, my group, that we worked on all these projects that I showed today. Of course, funding, computational time for this sometimes very demanding computational projects. And here is the Biomedical Research Foundation, our group, and I would also like to thank all of you for your attention.
Thank you so much. Thanks a lot. As always, I think the best about hearing your work is that you always talk about what is working, what is not working, so that it is helping others to, when you think about some project, okay, this may not work or this may work better, kind of takeaway. So thank you so much for that as well. That was a fantastic talk, of course. Thank you.
Oh, thank you very much for your kind words.
So we can start with Q&A. Deniz, you can also unmute yourself and
hello.
Hello.
Deniz is the co-host today.
Nice to meet
he's
you.
gonna deal with the Q&A. We can have the questions, and I can start with maybe. So a couple of proteins I also work with in my limited experience, and I know that they are very hard. For example, GTPases, they have many different states. Or I think you said FXR. I work with PXR, and then they are even to find with a normal docking MD procedure, it has an abundant the pocket is too big, and then it becomes very hard to predict. So my question is, some of the pitfalls, do you think it is because the systems are too demanding, to know the different states, for example, for GTPases?
Yeah. So what is the question?
So for the GTPase case, for example, you were saying that AlphaFold is not working because
I see. Okay, yeah.
Because it picks up different states, right?
Right,
and in the
right.
membrane, you don't have actually GTP or GDP bound. You just have another.
Yes, you have it bound, but the problem is the following with AlphaFold and with all machine learning algorithms. The problem is that AlphaFold and all machine learning algorithms can only tell you what they have been trained on. And AlphaFold has not been trained on the GTPase on the membrane because it does not have this data. Nobody has this data. So if it's not trained on a property, it cannot tell you this property. So it does not know what is the membrane associated structure. So therefore it cannot generate it. And also it's the same that I showed you in the protein language models in the end. The algorithm was trained on 9 protein superfamilies. If you ask the algorithm to give you an answer about a protein that was not belonging in these 9 protein superfamilies, the algorithm cannot give you an answer because there is no training data, so it does not know the answer. So that is my answer, that if the algorithm is not trained on, in the data set does not exist what you're looking for, then you cannot produce it.
In the first, I just go on. If anybody wants any questions, please feel free to unmute yourself or write it in the text. Also, Dr. Cornea mentioned that you can also write some career advice kind of thing, right? In the beginning, you
Yeah,
said that. So
sure. Yeah,
please, yeah,
absolutely. We can also discuss any thoughts you have about,
yes.
how you can choose an appropriate
Yes.
program or how if you go out abroad and etc.
Yeah. So in the beginning, you have these ligands which are very similar, right? And which force field you parameterize them with? Did you?
That is a really good question because we found that the accuracy of the method really depends also on many factors, but force field is one of them. So it depends on force field, it depends on sampling, it depends on whether water molecules will be there and other factors, but force field is one of the most significant ones. And the force field will produce an error inevitably. So the best you parameterize your molecules, the best results you're gonna have. So there are two ways. Either you parameterize the molecules yourself, which is pretty tedious, but if you have a serious project and you have a congeneric series, so the molecules are very similar, you can produce the parameters. There in this project, we used OPLS3 FEP+. So it is a very advanced force field that is a proprietary. And additionally, there is a tool that's called Force Field Builder, which specifically parameterizes the molecule. So in that case, in that sense, we found so far that Schrödinger with FEP plus and their force field is the most accurate that we could find so far. In later versions, because of course this is not for free, it's a commercial software, we found that GAF2 at the moment for us it's producing the next best outputs. That is free, of course, because of course they are also commercial.
I
Yeah,
see.
so GAF2, we use GAF2.
I see. Okay.
Amber, it is
Yes,
Amber for sure. Yeah.
yes. I think nowadays the shift is more GAF, right? Because I feel like before it was more like CGNFF, but nowadays the accuracy I think becomes better in the GAF.
It really
Do you have
depends
any?
also on the case. In some
Okay.
cases, maybe CGNFF will be more accurate one. Before doing these calculations, it's also good to do a benchmark to
Benchmark.
test which force field will give you for known results, for known ligands and known results, which force field will give you the best outputs or correlation with experimental, and then you choose the force field and you go to the unknown cases, hoping that you are getting predictability.
For the dimer case, did you have a starting point or did you just predict initially? Because you are putting it in the simulation, right? And then,
Yeah. Yes, of course. I mean, you have to start from there, and as you mentioned, the starting conditions are very, very important. We started from the crystal structure that was known at that time, the 5 VQ2 PDB-ID. This was our starting condition, but we found that in the course of the simulations, uh, almost all the known structures of KRAS were produced. So the starting condition didn't affect the later sampling that was produced.
okay, but the orientation is not changing drastically, right? I'm
Oh,
talking
it's
about
changing really drastically.
oh,
In one case, I can share my screen
yes.
again, and I can show you the RMSD. It was right here. So let me go to Zoom. So basically here you see this is like almost 180-degree rotations, 15 angstrom. It's very
Okay,
far.
I see.
So this was producing a structure where the GTP was at the interface of the two. And this was a structure that was also published by other people.
I see. And this is on wild type, right?
This was, we did with and without effectors. We also did the mutant. Here is a
Okay.
G12D mutant.
Okay. Okay.
Yeah, here wild
Uh,
type G12D.
like was there a case, for example, for the mutant? Because I work on rock, and then we had some like mutations, and then the activation system is getting accelerated or not. Do you think in this case mutants have some kind of effect on binding or making a more stable dimers or making a lack of it?
Yeah, I mean, we are still
Mm-hmm.
investigating this issue, but the mutants, they can have multiple effects, which is, in my opinion, different in every case. They can produce conformational changes,
Mm-hmm.
they can produce more stable interfaces, maybe they produce more stable protein membrane interactions. So you really have to look into
Mm-hmm.
what's going on. Of course, here we have Martini models, which
Mm-hmm.
is held together by an elastic network. Therefore, we cannot see conformational
Mm-hmm.
changes. So we would have to look into other factors.
Mm-hmm.
But yeah, every case is different, and we here in this project we have not yet concluded
Mm-hmm.
as to what are the differences. This is what we are doing right now.
Mm-hmm. But fantastic work. I mean, thank you so much.
Oh,
So there
thank
are
you.
there are a couple of questions. I can go on forever, like so I need to stop at some point. There are a
Thank you.
couple of
Yeah.
questions. Let me just read
Okay,
them for you.
which tools methods do you use for binding site identification? So here for the binding site identification within DREAM, we use the P2 rank, but routinely we use FPocket. FPocket we found has a very good correlation and predictability with experimental results. Yeah, so here it's a P2 rank, but we use FPocket as well. What are your strategies for ligand naming and calculating ligand RMSD after different docking tools? Ligand naming, we use, what do you mean? UPAC namings. You mean if I'm gonna name it from 1, 2, 3, etc.? I mean, everybody can have their own scheme.
Maybe he's mentioning about the top ones, for example. How do you
About
find
the
that? About the docking, after docking, this is what he's asking, right? Yes.
after docking?
So he can probably, I mean, he
Sorry,
can.
yeah, sorry,
Yes,
Yeah.
can you
sorry.
hear
Yes,
can
yes,
you
yes,
hear me
yes. Go
well?
ahead. Yes.
I can. I have a problem with this stuff. Sorry, and I just let you know. Can you hear me well?
Yes, please.
No, I. So I was actually trying to say that when we use different tools, especially for vitroscreening, according the reference ligand, every docking tool or different preparation change the ligand naming. That one totally affect our RMSD result. And for every tool, we need to sometimes do this manual stuff, but still I couldn't find any proper tool to make or
The
method.
name should not affect the RMSD. The RMSD is based on XYZ coordinates. If the XYZ are not changing, why would the RMSD change? It's not dependent on the name of the ligand.
Yes, for protein is so simple to adjust, but for protein alignment and calculating our ligand RMSD, always equivalent atoms are mismatching, and that one is changing. Is the thing.
Okay, I see. No, we use our own Python scripts, and there's no way around it. I mean, you have to do some coding. I see what you mean. Yeah, I mean, these are technical details that unfortunately are not solved by the algorithms or the people who produce the algorithms. And yes, in many cases, we have renaming of all the residues, all the not the residues, the residue numbers, renumbering of the residue numbers, renaming of the ligands. Yeah, we use our own in-house Python script. There's no other way around it, unfortunately. Hopefully, you can report this bug to the developers of the software and you can alert them that this is causing issues, and at some point in the future, they will fix it. But until then, you have to use your own, either with R, MD analysis, Python scripts, RDKit. I'm just citing a few of the tools that we are using.
Thank you.
Okay, there's only one more. What type of algorithm can I use to predict the binding pockets of a macromolecule without having the parent ligand? Okay, that's a really good question. So let's say that the person is referring to an apostructure. So basically there is a protein and there are no molecules. And we have a new algorithm for that to find the allosteric pockets where you don't find the orthosteric pocket, where usually it's not very interesting because orthosteric pockets have their own native ligands that bind very tightly, and because they are affected by issues of selectivity within the same protein family. So to use to identify other pockets, we use F pocket. And then we use our tool also to determine whether these pockets are actually viable, whether they are going to be functionally relevant. And this is our tool that is called AlloPockets that we expect to submit very, very soon. And maybe we can do another webinar next year about it when it's published. Yeah, why not? And I just wanted to say that there is two different things. One thing is to actually calculate the pockets, because on the surface of the protein you will find many different pockets. We use F pocket for that. It's a really good tool, I recommend it. But not all of these pockets are going to be functionally relevant. So you want to find pockets that will produce an effect to the activity of the protein, that will affect the function of the protein. So this is a functionally relevant pocket. And that's not so straightforward. That's why we created AlloPockets, and I'm happy to talk about it next year.
Perfect. Thank you so much.
Is there any more questions?
Okay. Well, thank you very much for
yeah.
having me today. Really enjoyed.
Thank you so
And
much.
send me the link of the presentation when you have it.
Definitely. Thank you so much. That was a really fantastic
I'm
talk.
so happy
And
you
then,
enjoyed it.
like, you know, it's like really a privilege to have you. We learn, I think I can talk for everyone. We learn a lot. Thank you so much.
Thank you very much for the invitation again.
Yes, thank you. And also thank you for all the people who were with us today, also throughout the year. This is the last webinar of the year. So it is great to finish it with you. Thank you so much, everyone. Thank you.
Bye.
Bye-bye.